Nice, it worked. All right. So I'm going to share my screen. That should make things a little easier to follow. Oh, and now it's doing the closed captions. So cool, cool, cool. All right. So let me go back up to the top. All right. So, like I said, we're talking about motion estimation using computer vision. Mentioned we're going to cover those three topics for our project 3. So motion estimation, structure for motion, and facial recognition. It's like I said, we sort of worked through all of the foundational topics. And now we get to kind of enjoy some more application stuff. So the idea is we want to determine an object's motion from a series of images. And the way we do that is the way we determine motion for anything, right? Where we have to solve Newton's equations. So the idea is, can we sort of take the kinematic equations for motion that we are also familiar with and apply them to pixels inside an image? And so at the most basic level, we're looking at if we have a pixel is in one position in frame 1, where is that pixel going to be in frame 2? Or conversely, if we look at its location in frame 2, we want to know, okay, how did it get there, right? Can we create the motion vector and sort of, obtain how it got there, right? Can we find basically the solution to those equations? And similarly, if we want to look at the intensity instead of just the position, we want to know, has it gotten closer to us or has it gotten farther away? And can we figure that out based off intensity? So we know something is moving in an image, and we want to kind of figure out where did it move to and how is it moving? So when we look at motion inside of the image, we're going to look at a couple different sort of versions. So there's this idea of rigid versus non-rigid. So if you're looking at an object in an image, you kind of have to decide if you're looking for something that does not deform, does not change shape, it's the same shape in every frame, which is rigid motion, which is pretty easy. Or there's the idea of non-rigid motion, which is where it can deform. So if you think like a human running, that's an object that deforms because the legs are moving, the arms are moving. So the size and the shape are changing versus if you just have a football, which is going to be football shape regardless of its motion. And then we have to figure out if we're looking at global motion or local motion. So is the entire camera moving? Is the entire point of view moving? So should every pixel move? Or am I only looking at one specific thing as it is moving? So for motion tracking in images, there are pretty much 4 models you can find and use. The first one is just a translational model. So you just x plus x prime, y plus y prime, right? You look at the delta of the pixel. And when you do a translational motion model, you are coming at it from the assumption that everything is moving in a straight line at a constant velocity. So you're only looking at how this object is moving back and forth or up and down in an image. So that's really the simplest one. And it's okay for 2D images, but it's not particularly useful because again, you're assuming everything is just moving in a straight line. There's sort of the Euclidean version of that where there's now a rotational element. So you're going to have kind of your delta x, your delta y, and your delta theta. So whatever you're looking at, the orientation can now change. So that's like if you have your person running, and so kind of the angle of the arms or the legs is going to change between frames. So translational motion is really only good for tracking rigid objects. Euclidean motion, you can do some dynamic stuff, assuming it's all rotational is the thing. So it's still moving in a straight line. It's just pointing different directions or moving in different directions as it goes. The one we are going to look at is called affine motion. And it's essentially a 6-parameter model where you've got your x prime and your y prime are some function of the prior x and y coordinates plus a constant. So this is much closer to how we would solve for motion in calculus with an integral and then taking a derivative. So the affine motion is really looking at the derivative of location over time, which matches the normal equations of motion closest to what we would usually see with, x plus 1/2 at squared. My master's degree is in physics, so I should be really embarrassed. I can't rattle those all off the top of my head. But you kind of think of affine motion as if you put translational and Euclidean motion together and started to look at a more continuous form of motion, or a smoother form of motion. You can kind of think about how it's going to make transitions easier, and you're going to kind of track smaller movements better. That's a more accurate way of doing it, the one we're going to kind of look at. And then there is projective motion, which is the homographic projection we talked about with image stitching. And so that's the good one, right? That's the one you would probably use for most real world applications, but it is also the most complicated and involves finding this projection and doing a translation between image spaces, which, like I said, we talked about with image stitching. It's a huge pain in the ass. And we're not really going to go through the linear algebra that goes into doing that. What I want to do for the class, for our take on this application, is to just look at affine motion. So, sorry. Okay. Let's see. So we don't want to do a bunch of homographic vectors. We don't want to do a bunch of 9-dimensional transforms. So we're going to stick with affine motion. And to do that, we're going to have to make some initial assumptions. One of the things we're going to have to assume is that everything is moving at a constant rate. So like I said, we're assuming when we're doing an affine motion estimation that there's no meaningful acceleration that will show up from frame to frame. It's basically the assumption that between every frame, you have moved at a constant velocity. And you can think about this by kind of hearkening all the way back to what we were doing when we talked about digital images in the very first place, right? A pixel is sort of a single, discrete, finite piece of information in space. And its neighboring pixel is its own fully discrete and finite piece of information. and nothing really exists between them. There's no continuous transfer between one pixel to the next, right? They just sit there and exist as their own themselves. So because we can't really continuously define what is in each pixel, we likewise cannot really continuously define their movement. So when we look at motion from one frame to the next, we're just sort of, we have to assume that it got there between frames at a constant rate. That's sort of the first assumption we have to make. It is a relatively safe assumption to make, assuming your images are not very far apart in time. You know, most of the time, if you're looking at a 32 FPS or a 60 FPS set of images or video stream, you can very safely assume there was no acceleration from one frame to the next. Because the other thing we are looking at when we look at this type of motion estimation, we're not predicting frame 1 to frame n. We are always working from frame 1 to frame 2, frame 2 to frame 3, right? Unlike sort of traditional motion in the real world, there's no history. So it's not, unless you want to put the work in, where it is in like frame 10 has nothing to do with where it was in frame 1, right? Where it is in frame 10 is based off of where it was in frame 9, and that was based on frame 8, and so on. Right, so we're not solving a continuous motion over time and space. We are simply asking, how did this pixel move? And when it moved, we assume it did it at a constant rate. And as long as we're not working with images that are sampled at like once a second or once every 5 seconds, we're okay doing that. All right. The other thing we are assuming when we are doing a fine motion estimation is that nothing is getting closer or farther away from us. That is an extra step you can add, again, if you want to do the work on top of just normal fine motion estimation. But kind of from the ground up at our base model, we're assuming nothing is getting closer to us or farther away from us. And we sort of make that assumption by assuming intensity is going to be consistent across frames. This can make it not great if lighting changes a lot in the way something is moving through the scene. So if you are looking at an image and there's some tree canopy, say, when an object moves from direct light into sort of a shaded area, say, and it gets dimmer, a fine motion modeling can struggle with that because it is assuming it's not getting closer or further away. And it typically makes that assumption by not looking at intensity when it is tracking motion. So if we go back and look at our equations, right, you can see it's still just an XY. There's really no concept of a Z or a third dimension in this kind of motion tracking. And you will see that come up a lot in actual applications of motion estimation, especially for robotics, that I have seen just because that's where I came from, where if you are doing computer vision to do something like a lane following task, when you do that, you're essentially tracking the motion of the lane inside the images. So every frame of the image, you're asking, hey, where is that lane marker? And so if it is nice and sunny out, then your motion model is going to find a nice bright white line or yellow line. If it is cloudy out, it is going to look for a different shade of white or a different shade of yellow. And so if you tune your lane detection to work in the sun, it's going to fail in the shade. And if you train it to work in the shade, it's going to fail in the sun, because a fine motion prediction can't really accommodate what it means for the brightness of something to change. And a really good example of this is I used to be a judge for a robotics competition that's held every summer at Oakland University, where usually it's teams of mechanical engineers for their senior project will bring a robot out and try to do this autonomous challenge where they're following lanes to go around a little course. And what happens invariably year after year is you would have a team come in the morning, right, and tune all of their motion modeling to follow the white lane. I have Professor Campbell to follow the white lane as it appears in the morning when the sun's coming up. And they'll do this and they'll get everything set, and then there'll be a lull while other teams are going. And it comes to be their turn, and now it's later in the day and the sun has moved, and the lanes aren't the same color essentially, or the same intensity, because now they aren't as brightly lit, and invariably the robot will just drive straight through a line because it was not able to accommodate a change in lighting. So that's something even now, driverless vehicles struggle with. We've gotten much better at it, but at the same time, doing two-dimensional fine motion modeling is based off of a constant intensity from frame to frame. Off topic, but did anyone see the article where they painted a road on a brick wall and a Tesla drove into it Looney Tunes style? Because that's now the centerpiece of my TED talk on why driverless vehicles are a dead-end technology, because supposedly the best one out there is just Wile E. Coyote with extra steps. And, if it goes from being really bright out to raining suddenly, it's not going to find lanes anymore. But anyway, I will climb down off my soapbox, sorry, and get back to this. So, like I said, we're assuming everything's going at a constant velocity because of the nature of the digital image. It is a non-continuous piece of data, and each pixel is also non-continuous, so we can't really say anything about what happened to it from frame 1 to frame 2, other than this two-dimensional motion model. And we're assuming constant brightness or intensity. And one thing about it is when we're using a fine motion modeling, we have to look at big things. We can't look at things that are small, that are only a few pixels, because it's going to get lost in noise. And we'll see in a minute kind of how that happens. But it's really a gross scale motion estimator. You can't track very small things with it because of the way we try to track things, which I'll talk about, like I said, in a second. So you can't use it for tracking a small thing. You can't use it for tracking or estimating the motion of things that are going, really, really fast or accelerating very, very quickly because of our assumptions. But it's kind of a nice sort of, it's your hammering your motion estimation toolbox. It'll work for the big stuff. It'll work for most of what you want, and it'll work very well with a relatively small computational overhead because it is only a 6-parameter model and not a 9-parameter homographic projection. And the other thing with a fine motion estimation is that we do not want to work with blurry data. So normally, like we've talked about all semester, when we're going after our to do edge detection and segmentation and those things, we typically apply a Gaussian blur so that we're kind of smoothing out things so that when we look for our gradients and our derivatives between pixels in the image, then they stand out a little better and we don't get a lot of noise. We've kind of smoothed things out so we only see the big changes. In this case, we kind of want the exact opposite. So because we want to see how each pixel moves from image to image, the more sort of unique it is, right, that may not necessarily be the best word, the more different or higher contrast it has between its neighbors in a broader neighborhood, the easier it will be to track, versus if something is, very blurry, then you're trying to see how like a big blurry thing moves, and you just can't really capture that. And that's another reason that, or not another reason, but another thing a fine motion estimation struggles with is blurry, right? If something is moving really fast, or if you think about your whole POV is moving, like if you're running around with a camera on the abandoned insane asylum from the ghost or whatever, when you swing back and forth really rapidly or an object moves through the scene very rapidly, it does not pick that up well and you end up with a lot of motion blur. So apparently here's where everything died, but still have these super sweet whiteboards I bought at the garage sale. So the best way to do, and I mean, there's never really an objective best, but in my opinion, the best version of a fine motion estimation is what's called block matching. And it is exactly what it sounds like. You're basically segmenting your image into blocks and then looking at how these blocks move across the image. So if you think about, right, got, right image, and there's your person, and there's your soccer ball. And so for a fine motion level, what we're going to do is divide this into blocks, right? We've done this a lot. We've seen it a lot with filters. It's kind of our standard. Here we go. We're going to start doing some TV. Let's start by looking at subsections. And these are usually going to be either 8 pixels by 8 pixels or 16 by 16. And that's just, for convenience and for the math and for back in the day when you think about 18-bit and 16-bit processors. So it's an arbitrary number, but it's as good of an arbitrary number as anything. And so what you do is you get all your little blocks, and then in your next frame, you look for that same block again. And what that means is you have the next picture here, other whiteboard I bought. So let's say you've got your next picture, and now your dude has run a little bit across the screen, and you want to take your block method again, where you've got all your 8 pixel by 8 pixel, And so then you take each block, right? So you start like here and you calculate some parameters for that block. This died while I was trying to write those out, so we'll talk about them a little more later. But what you do is you have some sort of measure for that block uh, right here. And so then in your next image, you do essentially a brute force matching where you take your block in your first image and then compare it to every block in the second image. Now, you don't always have to do it this way. This is sort of the standard out of the box where I want to take my block in my first image and compare it to every block in my second image in my frame two. So I don't have red, but I have pink, I guess. So we've got, in frame one, well, let's look at it this way. I've got frame one, and there's my block with the dude's head in it, right? So there's my block of dude and his head. And so then what I do in the next image is you just, right, compare that to every block in this image. And lo and behold, right here is where I find my dude's head again. So what I can do then is I look at the position here, I look at the position here, I take the difference. That was how I moved to get there. So that's my equation of motion for that block. Said you do it with a brute force approach where you just match your first block to every block, your second block to every block. There are a lot of heuristics you can use to make this go faster. It's actually not as slow as you might think, depending on how you implement it. But it's usually pretty easy to overlay some assumptions like, the block isn't going to move more than delta X or delta Y inside the image frame. So I can kind of limit my search to that area within the image. And then I can do kind of a moving box for every block to see if it's moved. And then you do essentially a sum of squares difference. So for, every pixel in frame one and every pixel in frame two, I calculate my parameters and then I compare them. And as long as they're within some threshold of each other, then I decide that, yes, this block in frame two was the same as this block in frame one. And so now that I know my delta X, delta Y, delta theta, I can now find, how it moved between those two frames. So it's pretty neat. It is easier than it sort of sounds when you set out thinking, I'm going to try and figure out the motion of an object in an image just by looking at it. Because, when you're in physics, you think about, you actually see the thing, put the car at the top of the hill and it drives down. And you measure things and you time things. And so when you're just looking at an image, you would tend to think that it would be harder to do if you're only looking at kind of this 2D grid of pixels. But based off of, everything we've kind of learned up until now in terms of how we can find the features inside the image, and then we can put them in our little blocks in our block matching. And then we can calculate our parameters that we know how to do. And we can compare them through a search, which we know how to do. Then we can find out how the stuff in block one moved from frame one to frame two. And then that will tell us, how that object is moving inside the scene. So I'm going to add the math and stuff to this and some code demos, assuming this computer continues not dying, which fingers crossed. And I'll have, sort of a sample problem involving motion estimation to add to project 3. So I'm going to wrap up there for today. Are there any questions or comments or anything? All right, dope. All right, thanks, guys. Sorry for the short lecture. I think I've got this sorted out now, but who knows? All right. Anyway, thanks for coming. Appreciate you guys, and I'll see everyone Thursday. All right. Bye.